All right, if you're in engineering, you've definitely spent some quality time with the bipolar junction transistor. You know, the BJT. It's like the bedrock of pretty much all electronics. So today, we're going to get our hands dirty and figure out how we actually take this little theoretical piece and make it do something useful, like amplify a signal.
But let's just get the elephant in the room out of the way. I know what you're thinking. We live in a world of plug-and-play op-amps, right? You can buy them for next to nothing. So why on earth do we spend so much time in class grinding through the math for a single solitary transistor? It feels kind of old school, doesn't it? Well, there's a really good reason for it, and it gets right to the core of how modern electronics are actually made. I saw this great quote on Reddit from a user named Titty2 that just nails it. They said that op-amp you just grab off the shelf, it's not some magic black box. It's an integrated circuit, an IC, and it's designed from the ground up at the transistor level. So if you can truly understand this one little component, you basically hold the key to understanding everything else. So that's our game plan for today. We're going to build this whole idea from scratch. First, why do we even care about these things? Then we'll tackle their biggest headache, non-linearity. After that, we'll see the clever trick engineers use to find a stable operating point. And finally, we'll get into the really cool part, small signals and big gains, and see how this all connects to the chips in pretty much every device you own. Let's do it.
All right, first things first, let's do a quick reintroduction to the star of our show today, the BJT.
So, the bipolar junction transistor. You know the deal. 3 terminals, base, collector, and emitter. The easiest way to think about it is like a tiny, super fast water valve. You use a little bit of effort, a small current into the base, to open the valve, and that controls a huge flow of water, a much larger current, from the collector to the emitter. And that right there, that control, is the heart of amplification. But, and this is a big but, it's not quite that straightforward in reality.
And that but brings us straight to the single biggest problem with transistors, the thing that makes them tricky to work with.
Take a look at this curve. You know how a resistor is nice and predictable? A straight line. What you put in is proportional to what you get out. Yeah, the BJT is not like that. The relationship between the input voltage and the output current is exponential. What that means in the real world is if you send in a beautiful, clean sine wave, what comes out the other end is not just a beautiful, clean sine wave. It's going to be a distorted mess.
And we're not just talking about one kind of distortion. Oh no, it's a whole rogues gallery of signal problems. You can get clipping, which is literally like taking scissors and chopping the tops and bottoms off your waveform. You get harmonic distortion, which pollutes your signal with a bunch of extra frequencies you never wanted. And if you dare to put more than one signal in, they can mix together and create all sorts of new garbage frequencies. It's a mess.
So, the big question is, how do we fix this? How do we take this wild, nonlinear component and make it behave predictably? Well, the trick is to find its happy place. We need to find a stable, quiet little spot for it to work from.
Okay, look at these curves. Think of this whole graph as a topographical map of every possible state the transistor can be in. Each one of these curved lines represents how the transistor behaves for one specific input current at the base. So by setting that base current, we're basically choosing which road we want to be on. But that's only half of it, because the transistor isn't acting in a vacuum. It's got a whole circuit built around it.
And that external circuit, the power supply, the resistors, it has its own set of rules. We can represent those rules with this straight line, which we call the load line. This line shows all the possible combinations of voltage and current that the circuit will permit. So where can the transistor actually operate? It's simple. It can only operate at the one point where its rules, the curves, and the circuit's rules, the straight line, intersect. That one single point is where everything agrees.
And that magic intersection has a name, the quiescent point, or just Q point for short. This is our anchor point. It's the calm, steady, DC bias of the circuit when absolutely nothing is happening. No input signal, just sitting there. And our job as designers is to choose our resistors so that this Q point lands smack dab at the middle of that nice, linear-ish, active region, way away from the ugly distortion zones. And just like that, we brought the chaos under control.
Okay, so we've established our stable home base, our Q point. Now we can do something really clever. We're going to use this stable point as a launch pad to finally amplify our signal.
And this is the secret sauce. It's called small signal analysis. Remember that crazy exponential curve from before? Here's the trick. If you zoom in, and I mean way in, on a tiny little piece of that curve right around our Q point, it almost looks like a straight line. So for a small AC signal that's just kind of wiggling back and forth on top of that big DC bias, the transistor basically pretends to be a linear device. This is a total game changer.
And because we can make that assumption, we get to use an incredibly powerful tool, the hybrid pi model. What this means is, for our small AC signal, we can forget about the complex nonlinear transistor and replace it in our analysis with this super simple linear equivalent circuit. It's just got an input resistance, we call it R pi, and a controlled current source. The power of that source is set by this crucial parameter called transconductance, or GM, and GM basically tells you how good the transistor is at converting an input voltage wiggle into an output current wiggle. And here's the key part. All the values in this simple model depend entirely on the DC Q point we worked so hard to establish.
So what this all boils down to is a clean, step-by-step process. Step 1, figure out the DC Q point. Step 2, use that Q point to calculate your small signal model parameters. Step 3, for the AC analysis, you pretend all the DC sources are gone and swap in your simple small signal model for the transistor. And boom, your messy nonlinear circuit just transformed into an easy-peasy linear one that you can solve with basic circuit theory to find things like gain, impedance, whatever you need.
All right, enough theory, let's actually put this to the test. Here we've got a classic common-emitter amplifier circuit. We know all the values, the resistors, the power supply voltage, and the transistor's beta. So let's just walk through the process and see what the voltage gain is.
And when you follow the steps, the math becomes really manageable. First, we find the DC base current, and that lets us solve for the collector current. There's our Q point. Done. From there, we calculate the small signal parameters R pi and GM. Now for the payoff. We plug those numbers into a simple formula for the output voltage, and we get a voltage gain of negative 3.04. It works! The theory gives us a concrete number. And that negative sign? Don't worry about that, it just tells us the output wave is flipped upside down compared to the input, which is totally normal for this kind of amplifier.
Okay, let's zoom back out. Why did we just walk through all of that math and theory? What's the big picture?
It all comes back to that question we started with. That op-amp you use in the lab, it isn't magic. It's not a fundamental particle. It's a highly complex little system. If you could crack it open, you'd find all sorts of clever circuits inside. Differential amplifiers, current sources, output stages, and every single one of them is built out of individual transistors, all designed using exactly the methods we just discussed.
And this is why it matters. Knowing this stuff is what takes you from just using components to actually designing circuits. It's how engineers who build custom ICs can squeeze out every last drop of performance, whether they need insane speed, almost zero power draw, or incredibly low noise. When a standard part just won't cut it, this is how you design something better. Heck, it's even vital in the digital world, because when you push clock speeds high enough, those digital signals start behaving like analog waves, and all these analog problems come roaring back. So I'll leave you with this question to think about. The basic ideas we talked about today, biasing to find a stable point and then linearizing around it, those are foundational concepts that aren't going away. But as our technology gets smaller and faster and more complex, what new, weird, nonlinear effects are lurking just over the horizon? And what kind of clever new models will you, the next generation of engineers, have to come up with to understand and control them?